Okay, welcome back to part 2 of topic 16, where we're looking at examples of electromagnetic induction and the application of Lenz's law, which basically says that anytime a current is induced, the magnetic field that's created because of that induced current will always produce a force that opposes the motion producing it. That's simple. So let's take a look at some more examples. We'll pick up where we left off in part 1. So here's another example. And this one again is very similar to Faraday's iron ring apparatus. Each of these coils has an iron bar in it to strengthen the magnetic field. So we want to know when the switch is closed and current flows through this solenoid over here, this guy here, solenoid X, what happens in solenoid Y? Okay, well let's check it. When we close this switch, here's what happens. Current begins to flow right here, right? Current flows here, up here, that means up the back, and that means it comes down the front, all the way across here like that, down the front, through the cell, and back again. Okay, and when that happens, that produces a electromagnet for solenoid X. And we use left-hand rule number 2 to figure out where the North Pole is. So we wrap our fingers around so that they curl down the front, and if you do that, your thumb points left. So there's your North Pole, which means this is a South Pole. So this South Pole is pushing out this way. It's pushing into solenoid Y. It's pushing into solenoid Y, which means that the force has to oppose the motion. So there has to be a force this way. There has to be a force to oppose that motion of that magnetic field. And that tells you that there is a South Pole on this end right here. That has to be a south. That's the only way to oppose the other South Pole. Like poles repel. Like poles oppose each other. So we know that's a south, which means this is a north over here. So we use our left-hand rule again, left-hand rule number 2 for coils. Thumb points to the right, because that's where the North Pole is. That would leave your fingers pointing up the front, like this, and down the back. So up the front, down the back would go this way, all the way around like that. So that means we get a momentary current. It's not a steady current, remember. It's only a current as long as the field is moving. So a momentary current from R to Q. You can see by the direction here. And it's all because of Lenz's law and those left-hand rules. So from R to Q, which means the correct answer is B. Correct answer is B. Okay, then we have this question. Similar again, only this time it's a magnet being pulled away. It's a magnet being pulled away. And what you do is this. If the magnet is being pulled away, that means that the force is opposing it. So the force is this way. Force is always opposite to the motion. Remember that. That's the key to doing these things. Force is opposite to the motion. So the only way to try to pull that magnet back, that means they have to attract. That tells you this has to be a South Pole right here and a North Pole right here. Okay? So in other words, the current, so let's do the current first. The current in the coil, if there's a North Pole at the right, like that, would have to move up the front and down the back. So up the front, like this, and down the back, like this. So that tells us that current is flowing from Q to P. So right away I can eliminate those. So I know it's from Q to P. Now, the compass needle. So this is a level 3 question, because this takes into account the magnetic field shape as well. Okay, so we got a couple of different areas of the course coming into one question. That's what we call level 3. It's a different combination than you're used to. So that's the case. The magnetic field around this will go like this, right? It goes all the way back around like that. So it goes away from the north, which would cause this compass needle to point that way. And that way happens to be to the right. So the compass needle would deflect so that it points right. So the correct answer is choice D. Okay? Choice D. Then, here's the one similar to dropping the magnet through the plastic tube and stuff again, only this time we're dropping the tube instead of the magnet. Okay, we got 3 rings. We got a plastic ring and 2 copper rings. Okay, now the plastic ring, remember, the plastic ring would fall normally. This one would be normal, because in a plastic ring there can be no current induced. So that one would fall normally. The copper one, though, would fall slowly. Okay, so the plastic one is normally, okay, and the copper one is slowly, the solid copper one that you see. Okay, so obviously the plastic one would hit before the copper one. Okay, so P would hit before Q. Now the question then is, what happens with this guy right here? It's a copper ring, but just look, there's a gap in it. This copper ring has a gap. That gap means that a current cannot flow. Okay, a current cannot flow around that copper ring because there's a break in it. So because of that break, that one would fall normally as well. Okay, that one falls normally as well. And the reason that it falls normally is because of the break in the ring. The break means no current. So that means that P and R will fall quickly and Q will fall more slowly. So the answer then is C. Okay, C. Make sense? It should. Okay, that's exactly the same as the one we talked about with the magnet being dropped through a tube. Remember I told you it was very similar to one of the rides at Canada's Wonderland. Some of you may have been on before, the drop zone ride. Okay, it's the same basic principle. Same thing makes it work. It's Lenz's law. The induced current produces a force that actually slows that ring falling. But the other two, because there is no current, they both fall normally. Now you might think the plastic one would fall more slowly than the copper one, but that's not the case. They fall basically at the same rate. Unless it was a really, really light piece of plastic, then air resistance would slow it down, but that would be making it more complicated than it needs to be. Okay, so that's that one. Let's try another one. Again, we've got a bar magnet being pulled out of a solenoid as shown. This time, though, they change it up a little bit. Instead of telling us what the pole of the magnet is, they give us the direction of the current instead. See that? Direction of the current is given. That's what these arrows here are. These arrows right here show that the current is flowing up the front of the solenoid. So if you use your left-hand rule on that, that would tell you that your north pole is right here for the solenoid because your thumb points to the right. So we know that X is north. That means that this one and this one are incorrect. So we've already got it down to 50-50 just by using left-hand rule number 2. Now we've got to figure out what would we have to do with that magnet to cause that to happen. What would we have to do to cause that to happen? Well, you'll notice that the magnet is being pulled out. What that tells you is that there's a force in. The force always opposes the motion. So there's a force pulling that back in. The only way for a force to exist pulling that magnet back in is if we had opposite poles, because opposite poles would be attracted, and that would pull the two together. That would be the direction of the force. It would be an attractive force. We're looking for an attraction. And the only way to get an attraction is with opposite poles. So that would have to be a south. That means the correct answer to this question is B. X, in other words, the end of the solenoid is a north, and because it has to oppose the motion being away from, then the magnet would have to be a south pole because it's being pulled away. Okay, so that's the logic that you use in these types of questions. Let's try one more. This one is not induction either. This has to do with something called magnetic levitation. Okay, and maglev for short. And you may have heard of maglev trains. Maglev trains means that there are two magnetic fields, and if those magnetic fields are strong enough, you can actually lift the train right off the track. And the beauty of that is, if it's lifted right off the track, there's no friction. And because there's no friction, that train can now go very, very fast. Very fast. So this one is a level 3 question again. Okay, it's a level 3. And what they're doing is they're asking you which design would produce the greatest repulsion. Well, first of all, the greatest repulsion would have to be the strongest magnetic field. And if you go back and look at the first part of this unit where we talked about magnetic fields and electromagnets, we said one of the factors that affects the strength of an electromagnet is the number of loops in the coil. So obviously this one and this one would give you a stronger field. So that right away eliminates these two. These are stronger, those are weaker. So we want the greatest repulsion. That's why we can forget about this guy and this guy. And that's the way I always tell my students to approach multiple choice questions. Okay? Get rid of the wrong ones first. Get rid of the ones you know are wrong because of certain clues that are in the question. And at least then, if you have to guess, it'll at least be 50-50. Okay? And you'll have a much better chance of getting it right. Sometimes you can eliminate 3. And if you can do that, then obviously the one that's left must be right. So that's a great way to approach multiple choice questions. So we know it's either A or D. So the only difference in A and D, if you look at it, is in A, we've got a north pole of a magnet close to the coil. And in D, we've got a south pole of the magnet close to the coil. But that's the only thing that changed. Look, the battery is still the same, the power source. The coil is still wrapped the same way. So the two coils in A and D are identical, but the magnet is switched. So one of these is going to repel, and the other is going to attract. We want repulsion, because we got attraction. That'll pull the train down to the track, which defeats the purpose. Then the train will not float on a magnetic field. So we got to find the one that is repelling. In other words, we got to find the one that has a north on top or a south on top. Okay, we got to see what the end of that coil is. Well, here's the way we do that. Let's do A. If we look at A, the magnetic field is created by the current. So our current flows this way. So across the front, like this. Okay, so based on that, we can use our left-hand rule number 2, fingers pointing to the right across the front of the coil, would produce our thumb pointing up, giving us a north pole right here. And this one does repel. So there's the answer. Okay, this is also a north pole right here, so these would attract. So obviously we don't want attraction, we want repulsion, so that would make that one the wrong answer as well. Okay, that's why. But this way, see, you only had to do the left-hand rule once because you already had 2 ruled out, so then as soon as you ruled out another one, you knew what the right answer was. Okay, that's the beauty of it. That is the beauty of it. All right, let's try this one. Now this one has to do with electromagnetism, but it doesn't have to do with induction. But I just thought I'd throw it in here because we're getting close now to the end of Unit 2. And one of the components of this course is there are STSEs. And they stand for Science, Technology, Society, and the Environment. And essentially, there's one for each unit. In Unit 1, it's called the Physics of Juggling. So it's all about projectile motion. In Unit 2, it's called the Physics of Cell Phones. And in the cell phone one, it's all about electromagnetism. And then in Unit 3, it's called the Physics of Movie Sound, and it's all about the photoelectric effect. So we'll talk more about that one later in the last couple of classes. But anyway, in this one, there's really two key things that you need to know that are in the STSE for Unit 2, the cell phone one. And that is, first of all, with cell phone safety. Like some of the risks, for example, with cell phones, and we don't know yet if these are real risks or if they're not. We don't know for sure. But one of the risks is long-term exposure to electromagnetic radiation. There is evidence that links it to cancer. So one of the concerns with cell phone use is if you're using a cell phone a lot, particularly if you've got one held up to your head, the electromagnetic radiation from that could be affecting the cells in your brain and could cause cancer. Now, we don't know for sure because there haven't been any studies that are long-term enough to actually tell for sure. But it is one of the risks. So that's one thing. And the farther away you can get that cell phone from you, so in other words, the hands-free stuff, not only is it safer for driving, but it's also safer in terms of exposure to the radiation. But so that's one thing. The other thing is the fact that cell phone radiation follows what we call an inverse square law. And an inverse square law means that the further away you get, okay, the further away you get from the cell phone, the weaker the radiation gets. In other words, the lower the intensity gets. And it works pretty much the same way as with sound waves. It follows what we call an inverse square law. In other words, the intensity of the radiation is inversely proportional to the distance squared. To the distance squared. So, which person here is getting the worst dose, right? Which one is getting the biggest dose of radiation? Well, person A is holding the phone 2 centimeters from his ear. Person B is holding it 6 centimeters from his ear. So obviously, person A, because the phone is closer, is more. Okay, A is greater. And the reason is because he's closer. The cell phone is closer to his head, to his ear. But how much greater is the question? Well, here's the answer. Okay, the radius is times 3, right? From 2 to 6, right? From 2 to 6 means 6 over 2, which is 3. So the radius is 3 times bigger. So the radius squared, which is 3 squared, is 9 times more radiation. Just by holding it those few centimeters farther away, you're getting 9 times less radiation from that cell phone. That's another reason why a lot of people like to use hands-free. All right. Now, the Bluetooth things that you clip onto your ear, that's not much better because they're sending out radio waves too, which is electromagnetic radiation. So that's not really accomplishing anything. It is a lot lower power, though, than the cell phone is, because that Bluetooth machine is only having to communicate with your cell phone, which might only be 10 feet away. It might be less than that. Okay, whereas the cell phone is having to communicate with a cell phone tower that could be a couple of kilometers away. So obviously your cell phone is putting out a lot more intense radiation than that Bluetooth headset would be, for example. Okay, so there's a type of question that you could get based on that STSE. The other one is all about the safety, right? The fact that The more you can reduce that exposure to the electromagnetic radiation, then the less your health risks are. And it's all because of that possible link. And again, it hasn't been proven, but there's a possible link between the radiation that comes from a cell phone, and we're not talking about like radioactivity, we're talking about electromagnetic radiation, which is similar, it's just a little lower energy. But it still can be harmful, so you do need to be aware. All right, let's try this one. Why is there an EMF induced between the wingtips of an aircraft moving at 700 meters per second in level flight directly above the Earth's magnetic North Pole? Now, this question, oddly enough, on the year this was on the public exam, this question actually got thrown out because of this term. EMF is not a term that we normally use in this course. So a better way to write that would be, why is there a voltage or a current induced between the wingtips of an aircraft? So when you think of it that way, because the aircraft is a conductor, right? The aircraft has an aluminum skin, which is a really good conductor of electricity. So as that aluminum skinned aircraft, in other words, that flying conductor, passes through the Earth's magnetic field above the North Pole, where the field vector is straight up and down, and the object is cutting straight across, okay, there is an induced current. Okay, the conductor, which is the plane, is moving relative to a magnetic field. That's the answer. That's all you'd have to say to get full marks for a question like that. The conductor, which is the plane, right? The plane is made of metal, that has a metal skin, an aluminum skin, is moving relative to a magnetic field. And the magnetic field is coming from Earth. And anytime you have relative movement between a conductor and a magnetic field, okay, that will inducing a current. It's that simple. It is that simple. Inducing a current. That's why. And that would induce a small current. Now, it's not a big current because it's not a strong magnetic field at the altitudes the planes are going to be flying. But it does still produce a current. Okay, other things that get affected by the Earth's magnetic field are charged particles coming from the sun. When they enter the Earth's magnetic field at the poles, they tend to begin to spiral. And as they spiral, they strike gases, ionizing the gas, right, giving it extra energy, ionizing it, and causing something called the northern lights, or the southern lights, the aurora borealis, or the aurora australis, down at the South Pole. Okay? Those things are produced by charged particles from the sun getting kind of trapped in the Earth's magnetic field and caused to spiral or corkscrew, which gives them extra energy and causes them to ionize gases as they strike the gas molecules, causing them to give off light, to glow. Just like when you pass electricity through a fluorescent tube or a neon tube, again, the gas gives off light. It's exactly the same principle. Only in that case, it's being caused by electrons, whereas the charged particles from the sun are normally things like alpha particles and beta particles and things like that. All right? Last question. Very similar to the one we just did. A spacecraft orbiting the Earth has a coil of wire in it. An astronaut measures a small current in that coil, even though there's no battery. So again, if there's no battery connected to the coil, then the only place a current could possibly come from is induction. So it's exactly the same type of explanation that we just used. Okay, the current is caused because the wire is cutting through or has relative motion to the Earth's magnetic field lines, thereby inducing a current in the wire. And on that question that year, that was worth 2 marks, just for saying that. It's an induced current because there's relative motion between a conductor and a magnetic field. It's that simple. Okay, it's all about Faraday's discovery. And that brings us to the end of electromagnetic induction and Lenz's law. So the next topic, number 17, will be the final part of Unit 2. And that's all about, again, it's still involving electromagnetic induction, but it's a special application of electromagnetic induction called an electric generator. So that will be the topic of number 17. So again, good luck with your studies. Work hard. Come back and view as many of these as you have time to do. Do as many old public exams as you have time to do, because that is an excellent way to study. So again, good luck with your studies, and